Data cleaning and preprocessing transform raw data into a form that AI models can use. This video explains why most AI work happens before modeling, and how cleaning decisions directly affect model behavior, accuracy, and reliability. Raw data is rarely ready for modeling. It contains errors, gaps, inconsistencies, and noise that must be addressed before learning can occur. In practice, data cleaning consumes the majority of time in AI projects. This reality contrasts sharply with the common focus on models and algorithms. Common data problems include missing values, incorrect entries, duplicated records, and inconsistent formats. Missing data occurs when values are absent due to sensor failures, incomplete forms, or collection errors. Not all missing data is the same. Sometimes values are missing randomly, while other times absence itself carries meaning. One approach to missing data is removal. Rows or columns with missing values may be discarded when loss is acceptable. Another approach is imputation, where missing values are estimated using averages, models, or domain rules. Imputation introduces assumptions. Poor assumptions can distort patterns and mislead learning. Outliers are extreme values that differ significantly from the majority of data points. Outliers may represent errors, rare events, or meaningful signals depending on context. Blindly removing outliers risks deleting important information, especially in anomaly detection tasks. Noise refers to random variation or measurement error that obscures true patterns. Noise cannot always be eliminated. The goal is often to reduce its impact rather than remove it entirely. Data normalization rescales values so that features operate on comparable ranges. Without scaling, features with larger numeric ranges can dominate learning unfairly. Common scaling methods include normalization and standardization, each with different assumptions. Categorical data must be encoded numerically because most models operate on numbers, not labels. Simple encoding methods assign numbers to categories, but may introduce unintended order. One-hot encoding avoids artificial ordering but increases dimensionality. Text data requires additional preprocessing such as tokenization, cleaning, and normalization. Preprocessing choices shape what information the model can and cannot access. Inconsistent units, formats, or conventions introduce hidden errors if left uncorrected. Deduplication removes repeated records that can bias learning toward overrepresented cases. Data cleaning pipelines must be reproducible to ensure consistent results over time. Manual cleaning does not scale well. Automation is necessary for large datasets. However, automated cleaning can hide errors if not carefully validated. Overcleaning is a real risk. Removing variability can eliminate meaningful signal. Cleaning decisions often involve trade-offs between simplicity and fidelity. Preprocessing is tightly coupled with model choice. Different models tolerate noise differently. Data leakage can occur during preprocessing if information from the future enters training data. Leakage often happens unintentionally through normalization or aggregation steps. Proper preprocessing respects training, validation, and test boundaries. Visual inspection remains valuable. Plots often reveal issues missed by automated checks. Documentation of preprocessing steps supports transparency and debugging. Cleaning choices embed assumptions about what matters and what can be ignored. These assumptions shape downstream predictions in subtle but important ways. Preprocessing errors are difficult to detect once models are deployed. Iterative refinement improves preprocessing as understanding deepens. Feedback from model performance helps identify preprocessing weaknesses. Effective teams treat preprocessing as part of model design, not a separate task. Robust preprocessing increases model stability across environments. Well-cleaned data reduces the need for overly complex models. Poor preprocessing cannot be fixed by better algorithms alone. Cleaning pipelines should evolve as data sources change. Monitoring helps detect new anomalies after deployment. The quality of preprocessing directly limits achievable performance. Good preprocessing supports fairness, reliability, and interpretability. The key takeaway is that preprocessing shapes what models learn and how they behave. Next, we examine data labeling and annotation, where meaning is assigned to data.